The Ethernet standards include standards for local area networks and wireless area networks. Ethernet uses wired communications, include a twisted pair, fiber optic links, and coaxial cables. These standards include the 802.2 and 802.3 standards. It supports data bandwidths from 10 megabits per second to 100,000 megabits per second or 100 gigabits per second. Remember that the data link layer has two sublayers, LLC, which talks to with the network layer, layer 3, and the MAC sublayer, which communicates with the physical layer and works with the physical layer. One of the jobs of this LLC sublayer is to place information on the frame that identifies which network layer protocol is being used for the frame, IPv4 or IPv6. It also allows for IPv4 and IPv6 to work on the same network interface media. The MAC sublayer uses the 802.3, 802.11, and 802.15 standards. This layer is implemented in the hardware and is responsible for data encapsulation and media access control. Provides data link layer addressing, which is going to be your MAC address. This just shows you a visual of how the data link layer is divided into two and the different standards for each one of the sublayers. The IEEE 802.3 data encapsulation includes the internal structure of the Ethernet frame, includes standards for the internal structure of the Ethernet frame, Ethernet addressing, which we spoke about in Chapter 6 and Chapter 3. This standards specify how the source MAC address and destination MAC address get added to the frames, and how they're used to deliver the Ethernet frame from Ethernet NIC to Ethernet NIC on the same local area network. The Ethernet frame includes a frame check sequence on the trailer used for error detection. The 802.3 MAC sublayer includes specifications for different Ethernet communications over the various types of media. The frame size can be anything from 64 bytes to a maximum of 1518 bytes. Any frame that's less than 64 bytes is considered a collision fragment or a runt frame, and it's automatically discarded by the receiving devices. Frames that are bigger than 1500 bytes of data are considered jumbo or baby giant frames. These frames are also discarded by the receiving device. These runt frames and jumbo frames most likely are the result of collisions and unwanted signals from interference. The size of the frame depends on the size of the data that is being carried by the frame, which can be anything from 46 to 1500 bytes. It also includes the size of each one of the fields that we're looking at right here. Now remember that what we're seeing right here is a representation of the code that is sent through the signals on the different media. This is for us to understand, but it will be sent as different codes. For example, the MAC address is a hexadecimal number, 6 bytes in length. And if you remember, 1 byte equals 8 bits of information. So this destination MAC address would be 48 bits of code that is being sent through the media. As the device receives these ones and zeros, it will know that the first 8 bytes will include the preamble and the SFD. This is the first 64 bits of information or signals, encoded signals, that it receives. This first 64 bits of information will tell the receiving device to get ready to receive a new frame. The next 6 bytes of information the device is going to receive is the destination MAC address. This will tell the device if this frame is addressed to this device. If it concludes that this frame, this following frame, or the rest of the information coming is destined to it, then it will continue to process the rest of the frame. Then it will receive 6 bytes of information, or ones and zeros, that will tell it who is sending this frame. What network card is sending this frame? Which NIC card? The MAC address is unique, and you can think of it like the serial number on the network card, which is embedded on the actual hardware. The next field, 2 bytes of information, will tell the device whether IPv4 or IPv6 is being used. Again, this is going to be 2 bytes and ones and zeros. But if we look at this frame through Wireshark, we're going to see a hexadecimal code that specifies which protocol is being used. This is the hexadecimal code that we'll see for IPv4. For IPv6, we will see this code. And for the ARP protocol, we'll see this code. Now we already established that the data that is being carried can be anything from 46 to 1500 bytes. This 1518 bytes assumes that there's 1500 bytes of data and includes the trailer, the type field, the source and destination MAC address. Data This is the information that the data link layer received from layer 3, which has already been encapsulated. It has to be a minimum of 64 bytes. If it's anything smaller than that, additional bits will be added to this field as padding so it reaches that minimum length. And if the receiving device receives anything less than 64 bytes, then it will know that it collided. It collided or there was interference. So it will end up dropping the frame. FCS is going to be on the trailer. This is one of the last bits that the device is going to receive. If you remember from chapter 6, this field here is being used for error checking. Remember that it uses a CRC code, which stands for cyclic redundancy check, and it's a summary of everything that should be on the frame. Remember that the sending device will calculate the entire frame. I'll do a mathematical calculation to create the summary, and when the receiving device receives this frame, it will also create another summary of what it received. And if the two codes do not match, then it will know that something changed along the way. And if the receiving device realizes that something changed on the frame, it will drop the frame. Why would anything change along the way? Again, it could have collided with other signals, or it could be corrupted by interference. This interference could either add or remove information from the frame. By now you should have learned how to convert from binary to decimal and from decimal to binary. Also, you should know that the IPv4 can be represented with decimal numbers from the base 10 number system that we use normally, or it could be represented with ones and zeros, the binary base 2 number system. IPv6 addresses and Ethernet addresses are represented using hexadecimal 16 number system. IPv6 addresses and Ethernet addresses are represented using hexadecimal. Right now, what you need to know is that the Ethernet MAC address consists of a 48-bit binary value. We use hexadecimal to identify the Ethernet addresses because a single hexadecimal digit represents 4 binary bits. For example, if you want to create the number 5 in binary, it's 0101. In hexadecimal would be 5. Now this hexadecimal goes from 0 to 9 and includes the letters A, B, C, D, E, and F. If you want to represent 11 in hexadecimal, you would use one character, the letter B. A 48-bit Ethernet MAC address can be expressed using only 12 hexadecimal values, instead of using 48 bits to represent the MAC address. The MAC address is used to identify the physical source and destination devices on the local network segment. This is done at the data link layer. And here's a visual representation of the different bits on the MAC address. You have 48 bits, 12 hexadecimal characters, each pair of hexadecimal characters being 6 bytes of information. All MAC addresses must be unique to the device or the Internet interface. The vendors that sell Ethernet devices must register with the IEEE to obtain a unique 6 hexadecimal code called the Organizationally Unique Identifier, or OUI. This OUI identifies the manufacturer of the network card and will be the first 6 hexadecimal characters on a MAC address. The next 6 hexadecimal characters are going to identify the card itself. So half of the MAC address, the first half is going to identify the manufacturer, and the second half is going to be the serial number for that NIC card. You can see an example on the screen. The IEEE has assigned Cisco a OUI of 0062F. This code will appear in every MAC address on every network card that Cisco has manufactured. Cisco has to make sure that the last 3 hex digits are unique on every network interface card they manufacture. The MAC address is sometimes referred to as burnt-in address because the address is hard-coded into the read-only memory. When the computer boots up, the network card copies its MAC address from ROM into RAM. And when the device is forwarding a message to the Ethernet network, the Ethernet header includes the source MAC address and destination MAC address. This animation is showing you that when the computers receive a frame, they will look at the destination MAC address and compare it to the MAC address that's stored in the RAM. If the frame received contains the same MAC address as the computer is going to de-encapsulate it and forward it to the layers above. If the frame does not contain the same destination MAC address as the computer, it's going to discard the frame and not continue processing that frame through the different layers. Just like IPv4 has broadcast, different Ethernet MAC addresses are used for layer 2 unicast, broadcast, and multicast communications. A unicast MAC address is the unique address that is used when a frame is sent from a single transmitting device to a single destination device. At the start of the communication, the device sending the frame most likely will not know the MAC address of the destination device. It will know the IP address, but it will not know the MAC address. In this case, it will send an ARP broadcast frame requesting the MAC address of the destination computer. Once the destination computer replies with its IP address and MAC address, then the sending computer will use the new MAC address information to route the frame directly to that computer instead of sending a broadcast. A broadcast MAC address is received and processed by every device on the Ethernet LAN, and the destination MAC address, all 48 bits, will be turned to 1. This will give you a MAC address that has all the hexadecimal numbers set to F. When a switch receives a frame with a broadcast MAC address, it will send that frame through every interface that has another device connected to it. A multicast frame will be received and processed by a group of devices instead of all devices or one unique device. When a frame is intended or addressed to a group of IPv4 devices, you will see this code on the destination MAC address. When a frame is intended to be received for IPv6 devices or a group of IPv6 devices, the MAC address for the destination is going to include this code right here. There are different multicast destination MAC addresses that are used. For example, when the encapsulated data is not IP data, such as spanning tree protocol, which we're going to cover later on, it will have a different specific MAC address. You will also have a different specific MAC address for multicast when using the link layer discovery protocol. Again, this is not something you need to know about right now. It's just telling you that there's different multicast MAC addresses that are used for different purposes. When a switch receives a multicast frame, it will forward that frame out of every port except the port it was received on. And then the computers that are part of the group that's intended for, that frame is intended for, they're going to process the frame and forward it to the upper layers. If a computer receives the frame and is not intended for it, then it will discard the frame. If you remember anything about the different classes of IP addresses there is, you'll remember that Class D IP addresses are set aside for multicast communications. And a Class D IP address will have a range on the first octet between 224 and 239. The range for IPv6 addresses is going to begin at FF00:8. Because multicast addresses represent a group of addresses, they can only be used as a destination of a packet. The source will always be a unicast address. If a switch forward every frame that it received through every port that it has, it would have too much traffic on the network and your network would probably end up crashing. This is why the switch uses MAC addresses to be able to route the frames to different devices. It makes its forwarding decisions based solely on the layer 2 Ethernet MAC address. The switch is going to have a MAC address table, which is going to use to be able to find which device is connected to what port. Initially, this MAC address table is going to be empty when you first start the layer 2 switch. Here's an example of the information that the MAC address table will have. We'll have the port number and the MAC address that's connected to that port number. As soon as it receives a frame from one of the devices, it will look at the frame and look for the source MAC address. It will write down that information on the MAC address table. So, for example, if computer A were to send a frame out and is received by the switch on interface 1, the switch will write down interface 1 and the MAC address for the computer that's connected to it. This MAC address will stay there for a limited amount of time. There will be a refresh timer, maybe set to 2 minutes or 5 minutes. For example, if computer A stops communicating and it doesn't send any more frames to the switch for more than 5 minutes, it will remove the MAC address for computer A from the MAC address table. If computer A sends information to the switch and the MAC address for computer A is already on the MAC address table, it will refresh that timer. This will be a setting that you will be able to change, but there's already a default on the devices, and that default is 5 minutes. If that frame that it received from computer A is meant for computer C, the switch is not going to know where computer C is located. So what it's going to do, it's going to send that frame out of interface 2, 3, and 4, and it's going to wait for a reply from one of the devices. As soon as computer C replies to the communication, the switch is going to look at the information on the frame and write down the MAC address from computer C along with the interface it is connected to. For the rest of the communication from computer A to computer C, the switch will no longer send the frame through every other interface. The switch will send the frame straight to interface 3, which is going to end up going straight to computer C. And again, the switch dynamically builds the MAC address table by examining the source MAC address of the frames received on a port. The switch forwards the frames by searching for a match between the destination MAC address in the frame and an entry on the MAC address table. Switch speeds and forwarding methods. The switch uses one of these two methods to forward information between the different interfaces: store and forward switching and cut-through switching. In store and forward switching, the switch receives the entire frame and computes the CRC. Again, the CRC code is going to be a summary of what's included on the frame. The CRC uses a mathematical formula based on the number of bits in the frame to determine whether the received frame has an error. If the switch detects that there is no errors, it will look up the destination address and then determine which is the outgoing interface and send it out of that interface. In cut-through switching, the switch will forward the frame before it processes the entire frame. The minimum information it will need will be the destination address of the frame. As soon as the switch reads the destination address, it will forward the frame to its intended destination. So store and forward switching checks for errors, which makes it more reliable, but cut-through switching will be faster. One thing to keep in mind is that if your network is using quality of service, it will require you to have store and forward switching enabled. There are two types of cut-through switching: fast-forward switching and fragment-free switching. Fast-forward switching immediately forwards the frame as soon as it reads the destination MAC address. Because it doesn't check for errors, sometimes the frames being sent are received with errors. This type of cut-through switching is the typical method used. In fragment-free switching, the first 64 bytes of the frame are stored before forwarding the frame to its destination. Fragment-free switching can be viewed as a compromise between store and forward switching and fast-forward switching. So to recap, store and forward switching stores information before forwarding it. The fast-forward switching method from cut-through switching does not store information, it just looks for the destination IP addresses and then forwards the frame. The fragment-free switching from cut-through switching does store the first 64 bytes of the information and then forwards the data if there's no errors found. To store the information on the frames, the switch is going to be using memory buffers. These buffers can also be used at the interface. The frames might be buffered or might be stored in a buffer if the destination port is busy because of congestion or traffic. The switch will store the frame until it can be transmitted if there's too much traffic on the interface. There's two memory buffering methods. There's port-based memory and shared memory. In port-based memory, each of the interfaces will have its own buffer. A shared memory buffer is used by all the interfaces on the switch, and then memory is dynamically allocated. Shared memory is preferred because it can store bigger frames and also because it's only used when it's needed. When two devices are communicating, they both have to be using the same duplex mode. This will be a configuration on the switches that you'll be able to change. You'll be able to set it to full duplex, half duplex, or auto negotiation, which will automatically check to see what the other device is using and switch to that mode. The speed or the bandwidth that is being used in the link also has to be the same on both devices. The speed will also be a configuration that you'll be able to change on the switch. It used to be that you had to create different cables to connect different devices. For example, if you wanted to connect a switch to another switch, you would use a crossover cable. If you wanted to connect a switch to a router, you would use a straight-through cable. And if you wanted to connect a switch to a computer, you would also use straight-through cable, and a router to computer will use a crossover cable. When you're building an Ethernet cable, you can use these different standards, 568A and 568B. If you're using the standard for 568A, you have the different cables inside the Ethernet cable arranged in this order. And for 568B, you would use this order here. When you want to build a straight through cable, both sides of the cable at the end will have the same standard. If you wanted to create a crossover cable, then one side is going to have 568A and the other side would have 568B. And depending on what devices you wanted to connect together, you would either use a crossover cable or a straight through cable. Most switch devices now support the Auto MDIX feature. This enables the switch to automatically detect the type of cable attached to the port and configures the interfaces digitally. For example, if you're using a straight through cable to connect a router to a computer, then the device, the router, if it has this feature, it would automatically change the pins so that the information is received as if you were using a crossover cable.